All right, in Statistics, Chapter 9, Lesson 2, estimating a population mean today. We had just finished up estimating the population proportion. Now we're going to do it for the same thing, but for a mean. The point estimate would mean the mean of the sample that you just took. That's the middle of our confidence interval. When we did proportions, we got z-scores, but for means, we will be getting t-values instead of z-scores. So we'll be doing an inverse t on our calculator instead of an inverse norm. We will get those confidence intervals, and we will also be able to determine how large of a sample do I need to have to be how much, like say 90% confident within 5 of the mean. Okay, so that's just kind of giving a little rough example of that. All right, so the point estimate, again, that's going to give you the value. It's a statistic estimate for the value of the parameter. Remember, statistics is about a sample and a parameter is about the population. So the point estimate is basically, it's a statistic, so it means it's coming from a sample, and we're using it to estimate, in this case, the mean of the population. So, for example, we have these pennies. They minted after 1982, and they were made from 97.5% zinc and 2.5% copper. The following data represents the weight in grams of 17 randomly selected pennies minted after 1982. So there's all the individual data values. So we treat the data as a simple random sample, and we estimate the population mean weight of the pennies minted. So to estimate we add all of them together, divide by 17, and there's my mean, 2.4641. So we call that a point estimate. In other words, I think the mean for the pennies, what they weigh, is going to be about somewhere around 2.4641 grams for pennies minted after 1982. Now, this was a little side note. These weren't originally in the notes from the company. I found that students didn't know how to get the t-value from their calculators. There is a table as well. If you want to learn how to use the table for it, just see me later, and I'll show you how to use a table. Most of my students prefer to use the calculator for this. All right, so this is a little side note before we go back to the notes for this lesson. It says the area to the right of a t-value is 0.15 with 10 degrees of freedom. So I'm telling you that this area on the right is 0.15. That's 15%. Therefore, this left area would have to be 85%. So what we will do to get this t-score then is we would do an inverse t, and we tell it the left area, which was 0.85, with the degrees of freedom of 10. The degrees of freedom is going to allow us a little bit of a room for error, is what the degrees of freedom does. That would mean this problem here had to have had 11 data set values. The degrees of freedom is 1 less than how many is in the data set. So 11 data values, 10 degrees of freedom, that's where we get that 10. All right, this one says, the next one is the area to the left of the t is 0.01 with 27 degrees of freedom. If you had 27 degrees of freedom, that meant you had 28 data values. Okay, you had 28 data values. The t-value, the area to the left of that t-value is 0.01 to 100th. So that's already the left area. So I would do inverse t of the left area, 0.01, and then the degrees of freedom of 27, and you push enter. So again, you guys are going to go to second distribution. And after you do second distribution, you're going to choose your inverse t instead of the inverse norm. All right, and you give it the left area, your degrees of freedom. You push enter, and it'll give you the values. All right, next one says find the critical t-value that corresponds to a 90% confidence interval with 17 degrees of freedom. So 90% would be in the middle. If 90% is in the middle, that means I got 10% cut in half. So that would be 0.10 divided by 2 would be 0.05. Or think that just as 10% divided by 2 is 5%. 5% is 0.05. So I need to do the left area of the inverse t. Again, these are inverse t's, not inverse z's, not inverse norms today. So the inverse t of 5% with 17 degrees of freedom. And that would be my critical value. Oops, sorry. All right, constructing the confidence interval. So again, get your formula sheet out. If you have to, pause the video and then come back to it after you get your formula sheet out. All right, now that you've got your formula sheet in front of you, please locate under Chapter 9 the formulas for the confidence interval for a sample mean. Now, one of the things that we have to have true is that, first off, the data has to be from a random sample. Can't be just all my best friends. I can't make conclusions from that. The sample size, if it's relatively small, then it's going to have the number in the sample still less than 5% of the population, just like proportions. And then the other thing that has to be is one of these two. It either has to come from a population that's normal, and they will have to tell you that, or if the sample size has to be greater than 30. If the sample size is greater than 30, then it really didn't matter if the original population was normal or not. We would still be able to use the confidence interval formula. So the confidence interval formula is going to use your sample mean. This is going to be your point estimate, plus or minus the t critical, which is going to be from your inverse t, times the standard deviation from the sample divided by the square root of n, which is the number in your sample. And again, the t sub alpha divided by 2, that's the critical value with n minus 1 degrees of freedom. So those same data values we had earlier, okay, and if you want to, you're welcome to put those into your, pause this, put all these numbers into the calculator, and then run a 1-bar stat on it. I'm going to assume you all can do that, and therefore then I'm going to have, there were 17 data values with the sample mean of and a standard deviation of, right there on the screen on the right for you. Now, we would need to know if this was normal or not. See, nowhere in the story does it tell me it came from a normal population. And since we have less than 30 in our data set, that would kind of concern me, because if there's not 30 in my data set, then I would need to prove that this was, not prove necessarily, but I need to make sure my data came from somewhere that was normal. Now, if I did my little normal, my QQ plot from the StatCrunch, I would do the little correlation to test it against the critical value. Remember, if the correlation was greater, then we would say it's from a normal population. The other thing you can do is kind of see if these points are all within this boundary, and if your box plot looks approximately symmetric, not very right skewed or left skewed, then you would assume that your data was from a normal population. So since these data values were all within that, this isn't extremely right or left skewed. To me, it just looks slightly right skewed, a little bit longer over here on the right than this left side, but all the points fell within the boundary here. So we're going to have to go with that this was from a normal population. Now, most of them on my test, I tell you it's from a normal population, so you don't have to worry about that, or there'll be more than 30 in the data set. All right, we're going to still, our goal here is to construct the 99% confidence interval. So I know the mean. Okay, we need to get this t. Now, we want to be 99% confident. That means 99% in the middle. If I have 99% in the middle, then what percent's left for the two tails? So 99% in the middle, that leaves you 1% for the outsides together, but you have to divide that by 2. So what we have there was the 99% was in the middle, so I wrote 0.01 divided by 2. I would do the inverse t of that with degrees of freedom of, since n was 17, it's 1 less than that, than 16 degrees of freedom. So that's how I got that t-score. So you would run an inverse t of 0.01, divide by 2, degrees of freedom of 16, and then hit enter. So again, that was under your second distribution, inverse t of 0.01, 1% for the two tails, cut in half, so divide by 2, degrees of freedom, and then you'll have your t-value. You plug that in, once with a minus, once with a plus sign. And make sure you list the lower one first and then the upper one second. So we are 99% confident that the mean weight of the pennies minted after 1982 is somewhere between 2.452 and 2.477 grams. So if a random sample of 225 audited estate tax returns, it was determined that the mean tax owed was $3,500. See, I already have n is 225. That means the sample mean, that's x bar, is 3,500, with a standard deviation of 2,500, so that's s. Construct a 95% confidence interval for the mean additional taxes owed. Okay, guys. See, we already have more than 30 in our data set, so I don't even need to test for normality at all. So n was 225. There was my sample mean. There's my standard deviation. Oh, I need to get this t. Guys, how confident do I want to be? I want to be 95% confident. If I want to be 95% confident, that means the middle 95%. Remember, that means then the tails are 5% cut in half. So 5% cut in half, inverse t of 5% cut in half with the degrees of freedom, in this case of 224. So that's how I got my t value, my t critical. We plug our numbers in. I do the minus first, and then I do the plus second. And again, just type the whole thing in straight across right as is. Don't try pushing enter in certain spots and all that, guys. Just type everything as is, once with the minus, once with the plus sign, and make sure you list the lower bound first and then the upper bound second. So determine the point estimate and the population mean and the margin of error for this confidence interval. See, this has already given me the lower bound and upper bound. See, the point estimate has to be right smack in the middle of those. The point estimate would be the midpoint of 18 and 26. So we add 18 plus 26, the midpoint's 22. Now, how far is it from 18 to 22, or how far is it from 22 to 26? That would be your margin of error. So my margin of error is 4. The last part is going to be to find the sample size. So just like we found sample sizes before, we are going to use now we have to use a z-score though, because we don't know n, so we wouldn't be able to do a degrees of freedom to get a t. So we will use the z only for determining the sample size when we're talking about the mean and confidence intervals. Otherwise, it's always the t. So we're going to still use the inverse norm for this. We're going to be given a standard deviation divided by the error rate, how far off we can be, and then that would be squared. All right, so how large a sample is required to estimate the mean weight of a penny manufactured after 82 with this many grams? See, the mean weight, that we're estimating the mean weight, and I want it to be within this many grams. That's the error. That's how far off we're willing to be. 99% confident. So I need to get the z-score for 99% confident. That means 99% in the middle. That means 1% for the tails, cut in half. So therefore, I'm going to do the inverse norm of 0.01 cut in half. That's how we get the z-score. Okay, I was willing to be off by that. And then it said the standard deviation. Where's the standard deviation given? Oh, there at the end, at 0.02, 200ths. Plug in all your numbers. And always round up. So we would need to interview 107. We would need to take 107 pennies to be able to be 99% confident of what the mean weight of the pennies within 0.005 grams. So if you have a proportion, provided that the sample size is less than 5% of the population, n times p hat times 1 minus the p hat has to be greater than or equal to 10. If these two conditions are met, you may proceed on to the confidence interval. For a mean, again, n needs to be less than 5% of the population. Then one of the two have to be true. The data comes from a normal population, or you have n is greater than or equal to 30. If these two conditions are met, then you may proceed on to the confidence interval for the mean. The sample size for the proportions, you use one of the two formulas. If I have a prior p hat, if I don't have a p hat. And over here is the sample size for the mean. Notice both of these here have the z-score on the bottom. This is the only one that has a t. So that t critical, y'all, is going to come from an inverse t, not an inverse norm. So these three, all of these z-scores here all come from inverse norm, but this t comes from an inverse t. All of them is the left area, and only on the t do you have a degrees of freedom. You don't have a degrees of freedom on the z's. And that wraps up your 9.2. So again, like I said, on your confidence interval, this right here is your point estimate, the x bar. This part down here after the plus minus happens to be your margin of error. Okay, the degrees of freedom is n minus 1. And good luck to you guys on this assignment. I'll see you guys soon.